In this video, I'll be walking through the latch circuits from the previous videos to show you how they work in Logisim, and we'll also use those latches to build a version of a flip-flop, which is how data is stored in registers and other memory components that we use for building sequential circuits. Here I have a Logisim implementation of the same SR latch that we saw in the previous video. And as was mentioned in that video, the initial state of the output from an SR latch is determined by the exact order in which the signals arrive from the R and S inputs. And so Logisim initially can't figure out what the output of this circuit should be, and represents that with an E for error state. But we can use the poke tool and, for example, turn the reset bit on, which should set the output of this latch to 0. When we turn the reset bit on, now it is definitely the case that the OR will be a 1, and therefore the NOR will be 0. And so that means that both of the inputs to the bottom NOR will be 0, it will output 1, and we have a stable output of the circuit, where the circuit is currently outputting 0, and if we now turn the reset bit off, the latch will hold the value that it was previously set to, in this case 0, and continue outputting that on the Q output. If we instead turn on the set input, that should set the output bit to 1, and it does, because this OR will now be a 1, so the NOR will output a 0, and that makes both inputs to the top NOR 0, and so the NOR will output 1. And so now our output bit is 1, and if we turn the set off, the latch will maintain its value. So this is, in general, the purpose and the reason behind the name of a latch. When we set it or reset it, the latch grabs onto the value, either a 0 when we reset or a 1 when we set, and will continue outputting that as long as the inputs are both 0. But since the intended function of this latch is to have its inputs either both be 0 or only one of them be turned on at a time, it helps to have some control circuitry around this latch to make sure that it never goes into the state where both inputs are 1. Because if both inputs are 1, then the exact timing of which one gets switched to 0 first will determine the output, and that's not a way that we want this circuit to behave. So we can go now to the D-latch, and we can add an SR latch component to our D-latch canvas. So R is the top input, S is the bottom input, and Q is the output. And until we either set or reset this latch, the output is red, indicating that the value that is being output is unknown. We can edit the appearance of our SR latch to label it as such. And we can also remove this decoration if we want. And now when we go back to the D-latch canvas, it's now clear what component we've placed on the canvas. Our D-latch has two inputs, a data bit and an enable bit. And we want to set it up so that the data bit becomes the value that is stored in the SR latch, but we also want to set it up so that the value stored in the SR latch only changes if the enable bit is 1. We start with a couple of AND gates, and I'll change the number of inputs, and I'll also resize the gate to narrow so that it fits better on the canvas. And now I'll make a copy. And since our goal is to ensure that the SR latch only changes its value if the enable bit is 1, by sending the enable bit to both of these AND gates and connecting the AND gates to the inputs of the SR latch, we ensure that if the enable is 0, the output of either of these ANDs will be 0, and so both inputs to the SR latch will be 0, and that means that the SR latch will not change its value because it only changes value when either the set or the reset gets turned on. Then for our data bit, we want to make it so that if the data bit is 0, we would turn on the reset input, whereas if the data bit is 1, we would turn on the set input. And we can do that by having a NOT gate, and again I will make it narrow. And if we send the data into the NOT gate for the top AND, now when the data is 0 and the enable is 1, this AND will output a 1, which will cause the reset to be turned on for the SR latch, and that will set the value 0 into the SR latch. Then we also want to connect the data directly to the bottom AND gate. And so now if data is 1 and enable is 1, then the bottom AND gate will output a 1, which will turn on the set input for the SR latch and cause the latch to grab the value 1. So let's put an output pin, which we'll call Q. And now, as soon as we turn on the enable bit, we should see that the latch starts outputting whatever the data was. We turned on enable, and so now, since data is 0, the latch outputs 0, and if we leave the enable bit on and change the data bit, then that toggles the output of the latch. Whereas if we turn the enable bit off, the circuit will continue outputting whatever it last latched onto, and now if we toggle the data bit, there's no change in the value being stored by the SR latch, because the enable being ANDed before we get to the SR latch is preventing this value from being passed on. And so if the data is 1 and we briefly toggle the enable on, now the circuit stores the value 1, and further changes to the data now that enable is off have no effect. Now that we have this D-latch circuit that allows us to store a bit of data, we'd like to use that within a larger circuit that stores intermediate values and then computes additional things based on those stored values. And so this means that we need a new component in our circuits, namely a clock. In a CPU, the clock is just a simple circuit that toggles on and off at regular intervals. In a modern CPU, it toggles on and off at a frequency measured in gigahertz, that is billions of times per second. And so that means that the clock switches on and off billions of times per second, and every time the clock switches on, that indicates the start of the next CPU operation. So if we want to build a CPU that executes a new operation each clock cycle, then we need to build storage circuitry that gets its input from the output of the previous operation and stores it, and then presents the data that it has stored as output that goes into the operation on subsequent clock cycles. And the problem with our D-latch as it stands right now is that as soon as we change the data input, that propagates through our latch and becomes the output. And so if we were to use this latch to build a register that stores a binary number, then when we enable this latch, the number being stored would immediately also be broadcast as the output of this circuit. And that could cause a problem if the output from the register is currently being used as input to some arithmetic operation. If that changes in the middle of a clock cycle, then that could mess up other circuitry elsewhere in the CPU. So we would like to build a circuit that uses our D-latches to store data, but doesn't change its output until the clock cycle changes, and at that point it will start outputting whatever data it has most recently stored. And the name for this type of circuit is a flip-flop. A flip-flop has 3 inputs, one for data, one for enable, and one for the clock signal. And it has one data output. And there are many ways of building a flip-flop, but one that we can do easily in Logisim is to use 2 D-latches. Again, I'll edit the appearance of the D-latch to make clear what sort of circuit it is. And we'll build our flip-flop out of a pair of D-latches. We know we want our latch to eventually store the data input, and so we can connect that up to the D-latch's data input. But now we'd like to ensure that the latch only stores a new value on certain parts of the clock cycle. Remember that the clock will be toggling on and off at regular intervals as the CPU runs. So what we can do is have the first latch only be enabled when the clock is 1, and the second latch only be enabled when the clock is 0. And this has the result that it takes an entire clock cycle for data to propagate through this pair of latches. Again, we'll use an AND gate, and we'll make it smaller and give it 2 inputs. And we'll AND together the enable and the clock to govern the enable of the first D-latch. And then for the second D-latch, its enable will be based on the negation of the clock signal. And now we can connect the data bits of our 2 latches. So right now, if we toggle the data, nothing happens because the circuit is not enabled. So if we turn on the enable bit and toggle the data, we still see no change in the circuit's output. And that's because the first D-latch is only enabled if both the enable and clock signals are 1. So if we set the clock signal to 1 while the enable is on, now the first D-latch is enabled, and so it grabs as the bit that it will be storing whatever is the current value of data. And if we were to change data, we would see that the output of that first D-latch is changing along with it. But of note, that change is not being propagated through the second D-latch, because that latch is currently disabled since we've negated the clock. So let's say that we want our flip-flop to store a 1. So data is set to 1, and now when the clock next toggles to low, that enables the second D-latch and causes the whole circuit to output the value that we were trying to store. Now at this point, if we change the data, it has no effect, and also if we change the enable, it has no effect, and that's because when the clock signal is low, the AND gate here always outputs a 0, and so this first D-latch is never enabled. And so in total, we have the result that this first D-latch only accepts an input when the clock is 1, and the second D-latch only accepts an input when the clock is 0, and so it will take a full transition of the clock going high and then going low before this flip-flop will output the data that we tried to store. Let's go through that whole cycle one more time to store a data bit of 0 and see how things change. If we set data to 0, nothing that the circuit is storing has changed. Even if the clock continues to cycle, nothing has changed because our enable bit is still 0. But if we turn the enable on, then the next time the clock goes high, that will enable the first D-latch. So the clock now transitions to 1. The first D-latch is now storing a 0, but the circuit overall is still outputting a 1. And when the clock now transitions to 0, that enables the second D-latch, which causes the circuit to output the 0 that's being stored in both D-latches. And now if we turn the enable off, subsequent toggles of the clock, even if data is changing, have no effect on what value the circuit stores. Going back to our main circuit, we can now add a D flip-flop to the canvas. again, I should edit the appearance so we know what circuit we're using. And in Logisim, we have a component that simulates the behavior of a CPU clock. It's found under wiring, and we can choose a clock signal. This clock signal can be toggled manually like an input pin, but we also have the ability in Logisim through the Simulate menu to set the frequency at which the clock will automatically tick. If I set it to 0.5 hertz, that means that the clock will tick once every 2 seconds. And now, if I enable ticks, we'll see that the clock circuit is on its own, toggling back and forth between on and off every 2 seconds. And so we can demonstrate the operation of our flip-flop by connecting up a data and an enable, and then connecting the circuit's clock to the clock input of our flip-flop, and now we'll connect an output. And as soon as we turn on the enable, then once we have completed a full clock cycle, the flip-flop will now be outputting the 0 that was given as the data bit. If we turn off enable and change the data, since the enable is 0, that means that the flip-flop will not change the value that it's storing even as the clock toggles. But if we now turn the enable on, then after one full clock cycle, we will see that the flip-flop is now storing and outputting a 1. If we change the data to 0 while the clock is low, then it takes another round of the clock ticking first high, then low, before we see that 0 as the output of the flip-flop. And once again, when we turn off the enable, any changes that we make to the data are not passed through to the output of the flip-flop. And so this ability to store a bit of data in a flip-flop and have the data that's being stored only change in time with the CPU's global clock signal will be the basis of how we construct a simulated CPU on homework 4.